It's an honor to introduce you Sven Prufer, who is a professional in the space business, and he's going to give you a introduction to spacecraft control under the title of Space Ops 101.
Okay, thank you very much for the kind introduction. Hello and welcome to Space Ops 101. My name is Sven Prüfer. I'm a mission planning engineer at the German Space Operations Center, which is a part of the Deutsches Zentrum für Luft- und Raumfahrt. And I will give you a slightly biased introduction to spacecraft control. It's slightly biased because, first of all, I'm working for a particular space agency, and secondly, because we will look at the whole thing kind of through the lens of a mission planning engineering. Unfortunately, the topic is pretty large, so we won't be able to talk about everything. In particular, we will not talk about launches. Launches are pretty amazing. I'd love to see one in real life, but we can't really go into that much detail because that's a very specific and particular topic. Also, we will not talk much about human spaceflight, and neither about entry, descent, landing. So, for example, landing on another planet. Of course, the combination of human spaceflight and landing on another planet would be very cool to see, but I can't just talk about it right now. Okay, so instead, we will deal with one of the main segments of mission operations. So in general, you distinguish three parts. There's one, the space segment. So this is everything that actually flies up into space. So in particular, a satellite or a spacecraft, including its payload, so whatever it is doing up there. Then there's the transfer segment, which is, all the launching business. And then thirdly, there is the ground segment. So we will talk mostly about the ground segment. So this is everything that actually takes place on Earth in order to command or use the spacecraft in space. Okay, the ground segment itself, again, splits into various subsystems. So one of them is the main player when you want to actually talk to your spacecraft. Those are the ground stations. Okay, so we will definitely need to talk about those. Secondly, we need to actually know where our spacecraft is and where it is going. This is actually done or described by the flight dynamics. Thirdly, space is at the same time very cold and also very hot, so there's the power and thermal subsystem. Then there is attitude and orbit control, which are responsible for telling the spacecraft where it should look at and for actually figuring out how it is oriented. Next, we need to actually talk to the spacecraft. This includes interpreting, receiving and interpreting the data. So this is part of the TMTC subsystem or the data system. And last but not least, that's of course the most important subsystem, that's the mission planning, which is responsible for scheduling spacecraft activities. Okay, so the talk will kind of follow the life cycle of a spacecraft. We will start with the launch and early operations phase, which is called LEOP for short. And there we will need to talk about orbits and flight dynamics, as well as how to actually communicate with the spacecraft. After that, we will talk about how we can test and validate our spacecraft very quickly, and then we will switch to the routine phase, so when we do the actual operations of whatever the spacecraft was designed to do. This includes data analysis, telemetry, and telecommands, so TMTC, and also mission planning. And then in the end, we will talk about, the end of the mission, so whatever we are going to do at the end when we want to dispose of the satellite. All right, so everything starts with the launch. Well, not quite. Of course, before that, we have a pretty lengthy phase of preparations. I will not actually talk about this, but this might take about something like 2 years in advance of the launch in order to prepare everything to make sure that everything is running smoothly. Once the spacecraft is strapped onto the rocket, it will get, flown into space, and there it will be separated from the launch vehicle. From this moment on, then it's flying by itself, and we need to actually control it. However, we don't really know right now where the launch provider will put our spacecraft. It might actually be on its final orbit. Yeah, so, for example, if it's a rather low orbit, or it might be a transfer orbit to its final target orbit if it's actually further up. Once this is during this launch, there's actually a second control center. That's the one for the spacecraft. This is actually the control room K1 of the German Space Operations Center, and it kind of looks like you expect a control room to look. So in particular, there are many screens. On average, everybody has like 4 screens. There are large ones for showing an overview of what's going to happen, and there are many small yellow signs. These yellow signs denote the various positions of the operators and the engineers. At the back in the center, there is one position that's called the flight director. The flight director is the person who is in charge of the operations. So whenever there's something that needs to be confirmed, needs to be done, that needs to be decided, then he is the last operational person to actually confirm the decision. Now, in principle, right after the spacecraft is separated from the rocket, this control room actually takes over. However, there are a few subtleties here. In particular, right after separation, the spacecraft is somewhere. We kind of know approximately where it is because we planned this beforehand, but we don't know the precise position. We first have to acquire a signal. We have to find it in space and have to set up a connection. In order to understand this, we need to talk a little bit about orbital mechanics. So first of all, why does the spacecraft not fall down? Well, if you look at the ISS, so the International Space Station, it flies at an altitude of about 300 to 400 kilometers, where the gravitational force of the Earth is still about 90% of the one at ground. This means that you really need some horizontal speed in order to not fall down to Earth. So you need to go really fast. 7.9 kilometers per second, that's the speed that you actually need in order to not fall down on the ground. So if you're a bit higher in some orbit, then you need a bit less speed actually, okay, because you're farther away from the Earth. Okay, so we need to go very fast. Good thing to know. Secondly, we need to know at which distances we will actually be flying our spacecraft. So this is Earth, obviously. In particular, the following picture will actually be to scale, approximately. So one possible place where you can put your spacecraft is low Earth orbit. So that's the region below about 2,000 kilometers altitude above ground. However, 2,000 is already pretty high, so very common are altitudes of 600 kilometers, 500, 700. This is a place where you mostly do scientific experiments, in particular Earth observation. Okay, so there are many satellites, scientific satellites that actually try to take pictures at various frequencies of the Earth. And also this is a place where you do reconnaissance. Okay, then there are actually a bit higher altitudes. For example, there's a medium Earth orbit. So the drawn circle is actually at an altitude of 20,000 kilometers, and this is mainly used for navigational satellites. So think GPS or Galileo, the European version. And then there's another very common type of orbit, that's the geostationary orbit. This is at an altitude of about, or pretty much precisely 35,786 kilometers above ground. This is chosen in such a way that the orbital period, so the time it takes you to fly once around the Earth, is 24 hours. This has the advantage that the movement of the satellite is actually synced up with or synchronized with the rotation of the Earth, meaning that your satellite is kind of always at the same position as when seen from Earth. This is particularly important for TV satellites because, well, imagine you would have to actually move around your TV satellite dish all the time just because the satellite is moving. Instead, you only have to fix it once, and then it's pointing in the right direction. Okay, and this is also a very common place for communication satellites for the same reason, because we actually want to have a fixed position in which we have to look. Okay, in order to get there, for example, on geostationary orbit, it's possible that the launch provider will actually put us in some kind of transfer orbit. Yeah, they usually don't look like circles, but rather like ellipses. And in such a case, we would need to do additional maneuvers. Yeah? So we are on the red circle, we will fly outwards, but at some point we'll touch the geostationary orbit, so the black one. But in order to not, kind of fly back to Earth, we will have to accelerate. So this is a maneuver that we have to execute somewhat at the beginning of the mission in order to, reach our geostationary orbit. Okay, so the system that actually deals with these considerations, calculations, etc., that's the flight dynamics department. So their tasks are in particular orbit determination. There are various ways to do this. For example, very often you can actually ask the satellite where it is, because it has GPS on board, at least if it's a LEO, so a satellite in low Earth orbit, so it actually knows where it is. Or you can do ranging, which we'll talk about in a few seconds. And from this you can calculate the orbit. Once you have the orbit, you also want to know where the satellite is going to be located in the future. So you will do orbit propagation. Next thing, we might have to execute some maneuver to actually stay where we want to be, or to get where we want to be. So we need to calculate in which direction we have to thrust. We have to turn on our thrusters for how long. This is also done by flight dynamics. And the fourth point is, we have to talk to the satellites, so we actually need to see it in order to do this. And flight dynamics can actually calculate the times and the positions, or the directions rather, where the satellite's going to be. And you can see all of these tasks are pretty numerical in nature. Yeah, it's hardcore mathematics, numerics, meaning that you actually want to use some tools that are very well battle tested, so to speak. And one of the most common programming languages for numerical calculations is, of course, Fortran. Okay, so that's really a place where Fortran is still being used, actively being used, because these libraries are just working the way they're supposed to work, so nobody really wants to switch from there, because they're just very good. Okay, now let's go back to the control room. We have talked to our flight dynamics department. They have told us, the satellite's going to be at a certain position at a certain time, or at least that's where we expect it. So the next thing we need to do is we need to establish a connection to the satellite. And for this we need a ground station. The picture you see here is actually the ground station in Weilheim, that's in Bavaria. That's sort of the main ground station that we use. And it knows where to expect the satellite, so it's a certain direction. It should appear at a certain time above the horizon, and then it tries to establish a contact. This first acquisition, it is called, is the first contact of the spacecraft after the separation. And this is, of course, a crucial moment. Now, once it has established a connection, it tries to do various things. So first of all, it needs to downlink some data. So download, but it's called downlink. This includes telemetry, so descriptions of the state of the spacecraft, because we want to make sure that the spacecraft is actually still working after the launch. And then later, this also includes downlink of payload data, for example. So think pictures or whatever it was that the satellite was supposed to measure or to take. And then it will also uplink some stuff. So, for example, commands, because we want to tell the satellite to do something. But this might also include, for example, software updates. Okay. Right. And one other thing that the ground station can do is ranging. Ranging means that, you send a package or a packet to the satellite from the ground station. This travels with the speed of light. Then the satellite will actually reply to that signal or to that packet, and then the answer will fly. Will go back to the ground station. And if you measure the time, and if you know how long the satellite takes to actually react to such a packet, you can calculate the distance from the ground station. If you do this several times, then you get kind of like a radial distance profile, and from this you can really deduce the orbit of the satellite. Okay, so let's look again to Earth. There's a ground station. It's actually located at the North Pole here. So that's on top. And there's a satellite. The satellite is not to scale, just in case you were wondering. And it's actually flying on an orbit which is 600 kilometers above the ground. This is actually to scale. Now, the signals of the ground station, they actually have to pass through the atmosphere, meaning they are attenuated quite a bit. So you have a finite range of the ground station signal, and this is drawn here. So the red circle is an approximate range of the ground station, and this intersects the orbit of the satellite only at a certain time interval, okay, or a certain interval of the orbit. In particular, we can look at some numbers here. If you have a satellite at 600 kilometers altitude, you get a 90 minutes period, approximately 90 minutes period around the Earth, and the portion of the orbit that you actually see the satellite from one given ground station is 10 minutes long. Okay, so this means we would expect to see the satellite every 90 minutes for 10 minutes. Okay, and this is when we have to do all the downlink and uplink. Unfortunately, it's a bit more complicated because Earth actually rotates. This map of Earth actually shows the ground track of the satellite. So that's the projection of the satellite onto the ground. So that's the red line. And the problem is that after 90 minutes, the satellite returns to the position where it was before. However, Earth has actually rotated by some amount, like 90 minutes divided over 24 hours. This is why the ground tracks actually don't close up. So instead, you get these kinds of stripes. Over Europe, you see WHM, that's the Walheim station. It has a certain range. That's the circle-like black line. And you can see that usually you have two contacts with the satellite per rotation. Okay, so the third pass will already be outside of the range of the ground station. Okay, so you actually have even less contacts than what I said earlier. This picture actually shows the same situation from the top, so from North Pole. You can see that there are actually circles, so all the distortions that you've seen on the earlier slide was due to the projection that was used for the map. Yeah, so this is sort of what it actually looks like if you look from above the Earth, but the other one is the typical maps that you see. Okay, so now we have found our spacecraft, we want to talk to it, so we need to actually send a signal there. Now let's think about which kind of frequencies we might use for this communication. Well, first of all, we noticed that there is, for example, water vapor in the atmosphere which absorbs parts of the electromagnetic spectrum. So, for example, here at around 23 gigahertz, there is an absorption peak due to water. And the higher frequencies we use, the more actually gets absorbed. This means that we kind of want to restrict our frequency usage to actually lower frequencies in order to get a higher range. But then we also have, maybe less data rate. So in spacecrafts, you usually use actually the lower part of the graph that's shown here, usually even below what is shown at all. So this starts at 10 gigahertz, and you use even less frequencies or lower frequencies. For example, you might use UHF, so amateur radio, at 430 megahertz. You might use L-band, 1 to 2 gigahertz. In particular, the main carrier frequency of GPS satellites is in this range. Okay. Then there's S-band, so that's a very typical frequency range from 2 to 4 gigahertz, which is used for the actual commanding of the satellite. Yeah, so this is an important frequency for us, or band for us. Then there's also the X-band. So X-band is higher frequency, so we expect even higher data rates, and this is usually then used for payloads. Okay, so if you have a lot of data that you want to downlink, for example, a picture that you just took, from your satellite. Also, this is being used for deep space missions. Then there's Ku-band. Ku-band is used for TV satellites. And Ka-band. So this is now slightly above the local water vapor absorption maximum. So this is pretty cool. There you really have high data rates. It's being used for various applications whenever you need a high data rate. However, there are some mechanical difficulties, because you have directional antenna, so this is slightly non-trivial, but it's being used more and more often. Now, if you fix such a frequency and you talk to the satellite, you of course need to modulate some signal on top of that. You need some protocols which do some level of error correction, etc. So I will not talk about this, but in principle there are very specific standards for space that are being used in order to assure that signals that you send or that you receive actually get received. Okay, right. So we can now talk to our satellite. We have acquired a signal, so we switch back to the control room. In the control room, we are now very happy. So we have done the first acquisition. This is actually when people hear applause. And then afterwards, there are a few things that are left to do, actually. Now the work starts. So, for example, the satellite was actually running on battery during the launch and afterwards. But it needs, of course, some new power. So for this, you need to deploy solar panels. This is done during the LEOP. Also, you might need to deploy antennas. I showed you various frequency bands, and usually satellites actually have several antennas and using several bands for different tasks. So the commanding might be done on the S-band, but the actual downlink of the payload data might be on X-band. For this, you need an additional antenna, so this needs to be deployed. Also, this is the time when you do all the other maneuvers in order to reach your final orbit. And you start switching on other components of the spacecraft. This might include, for example, star trackers. So star trackers are essentially cameras that just take pictures of the sky, so of the stars, and they compare them to some onboard database of known star positions. And this way, the camera can figure out in which direction it is looking. If you know how the star tracker is actually mounted on the spacecraft, you can then deduce how the spacecraft is oriented. And this is important, for example, if you want to take a picture, then of course you need to know where have you been actually looking at. So you need something like a star tracker. Another thing that you would switch on or actually spin up during a LEOP would be a reaction wheel. So reaction wheels are essentially gyros that just rotate very quickly. You spin them up, and the idea is that this stabilizes the spacecraft. Because you actually want to control the rotations in most cases. Okay, so now we hope that everything was working perfectly. We launched the spacecraft, but unfortunately, not always everything goes perfectly. So let's maybe dig into some example. This is TVSat-1. Well, I don't have a picture, but there was a satellite, TV satellite from 1987, and everything worked as we described. So we got the first acquisition, we got some telemetry from the spacecraft, but unfortunately, the solar arrays turned out to be only partially deployed. That's of course a problem, and we need to diagnose this, and we need to fix it if possible. So the first thing you have to know is that you kind of can't really necessarily trust all the data that you get. Yeah, you have to confirm that whatever you are seeing is actually the case. So you have to use additional sources. For example, in the case of a solar array, you can actually check how much is the power output. Is it actually less than expected if it was deployed? And it turned out, yes, there's not enough power. And secondly, once you notice this, you can actually send the manual deployment command again. Yeah, so it's possible that the automatic solar panel deployment didn't work, so we just tried again. Unfortunately, this did not work, so it still seemed undeployed. Now you start thinking, well, what are we going to do? and you consult usually the satellite manufacturer. The satellite manufacturer actually also sits in the control room during the LEOP, because there happen to be many questions, so you need somebody on hand. And they suggested, or the people who operated the satellite, they suggested various tests to figure out what was wrong with TVSat-1. And I want to present just two of these things you can try. One is you can orient the spacecraft or the satellite such that it is at a 45-degree angle towards the sunlight, and then you start rotating it. If you do this carefully and you measure the power output of the solar arrays, you can actually estimate the angle that the solar array was deployed. So they did that, and they figured out, well, they're completely not deployed, so less than 2 degrees actually. Okay, so that's a problem. Then they did various other tests, and they came up with one possible problem, and this is that there might be the actual stirrups, so the black boxes in the picture, which keep the solar array attached to the satellite during the launch, that they might still be there. In principle, they should have been fired off or removed, and then the solar array should deploy. But it looked like they were actually still there. So one thing you can then try is, well, you can again rotate the satellite in such a way that the stirrups will cause a small shadow over the solar array. This will reduce the power outage again, the power output again, just a tiny little bit, so you might be able to measure this, and this way confirm that the stirrups are still there. Turns out this was not actually really well measurable, so this didn't work. However, they were still able to deduce it was probably the stirrups that are still there. Once you've diagnosed the problem, you want to solve it, of course. So let's see, how can we recover such a situation? And this is sort of where you can, well, just follow your creativity and come up with arbitrary solutions and see whether you can actually try them. So one thing we can do is we can spin up the spacecraft. If we do this very fast, we will have a very strong centrifugal force, so maybe an acceleration of about 1 g, and this way we might hope that we loosen the stirrups. Another thing you can try to do, you can use your main engine to actually accelerate the spacecraft in a pulsed way in order to excite resonance frequencies of the stirrups. Okay, so hopefully this might actually loosen the stirrups. Another thing you can try to do is you can command the spacecraft to heat up and to cool down in some ways, and this way actually also loosen the stirrups. And the last thing you can try is you can, well, kind of just try to shock the whole thing. So, for example, you could deploy an antenna. In this particular case, this was the main antenna, which was actually stuck beneath the solar array. So you try to deploy this and hope that the force actually pushes the solar array open. Yeah, unfortunately, none of those worked. And this was an unsuccessful recovery of a satellite. So in particular, the main problem was that, well, this was a TV satellite, so it really needs the antenna, but the antenna couldn't deploy because of the stuck solar array. So in this case, this did not work, but usually, of course, this works, and people are coming up with very creative, very interesting solutions to all kinds of problems and get things running. All right, so once we have our spacecraft in some kind of safe state, we kind of conclude the LEOP and we start testing the actual properties of the spacecraft. This is called the commissioning phase or in-orbit testing of the payload. So this usually takes longer than a LEOP, might take several months, depends on what type of mission you're looking at. This is when you actually start or switch on the payload, and when you also verify that the payload is working as expected. Okay, so in the picture you see a geostationary communication satellite. So its main payload are the communication arrays, or the antennas in particular. So for example, you might want to actually verify that the antennas are working properly after the launch. Yeah? So during launch they get shaked up, and it's really pretty intense. So you want to make sure that they are working properly afterwards. So for example, one thing you might want to do is point the satellite at your ground station, you measure the strength of the signal that you receive, then you move it slightly, you measure again the strength, and this way you kind of get a pattern of the antenna, okay? And this is a property of this particular antenna that you might use later. Another thing that you do during this time is you check out redundant components of the satellite. So, for example, if you have an Earth observation mission, as I already mentioned, you need to know where you're looking at. So you need, for example, GPS or star tracker. Now, if that fails, you obviously have a large problem, because now suddenly you don't know where you were taking photos or images. So usually there's quite a bit of redundancy on satellites. So there are two GPS transmitters, or receivers, sorry, and then you can actually switch between them. And during this phase, you will test that they are working properly. Okay. So let's suppose we have done this and everything is working as expected. Then we start with the routine phase. The routine phase is sort of the main phase of the operation. So that's when you actually do the science experiments, or you start offering communication services, or whatever it is you're doing. This picture is a picture of the mission Terza Tandem X. So those are two radar satellites flying in low Earth orbit, and they can actually make three-dimensional maps of the ground by sending a radar signal and then receiving it. And because they're flying in close formation, so something like a few hundred meters apart from each other, they actually get this kind of stereographical 3D information. Okay. And during the routine phase, a scientist would actually order a data take or a picture of this kind somewhere, maybe online, and then somehow the mission would actually command this, or the command center would command this data take. It gets downlinked, and then the result will actually given to the scientist. Okay, so this is the main phase of the spacecraft life, so where we do the payload operations. By the way, this picture is a picture of a joint American-German mission. That's the GRACE follow-on mission, two satellites that have a microwave or a laser link between them, and they measure the distances in order to, variations of the distances in order to deduce the gravitational field of the Earth. Last year at 34C3, there was actually a talk about the predecessor mission here, actually probably in this room. Okay, so this is a time when we do our science experience. Furthermore, we actually monitor the spacecraft, of course, because we still need to know what's happening. Is it working properly? We will, of course, continue to handle contingencies, but hopefully there are none anymore. And we might also adapt to new mission requirements. So, for example, you could actually try to devise new kinds of experiments on a flying satellite, and for that you might need to upload new software, which is also done during this phase. Another issue is that a spacecraft actually ages. So, for example, a battery might deteriorate. Yeah? So its total capacity actually gets smaller over time, so you need to adapt to that. For example, if there's less power available, then you can actually do fewer data takes, something like that. And you need to monitor this and react accordingly. Okay, so how does the monitoring work? Well, that's part of the TCTM and the data subsystem or system. And the idea is that the spacecraft actually measures various properties that it has, or that describe the state all the time. So we have a time series of binary data and also of numerical values. So for example, here the plot shows the temperature of a certain part of the spacecraft over time. But remember, we don't have this information available live. We only get this once we actually downlink it, okay? And then we get a huge part of the data at once. Okay, so this describes the state of the spacecraft, and there can be lots of parameters. So for example, 20,000 telemetry parameters for one spacecraft is possible. If you measure something once every second, you do this for a few years, 20,000 parameters, this means that you have a lot of data. So obviously you can do a lot of data analysis, time series analysis with that. You can do anomaly detection, telemetry prediction, or detecting errors or problems within this data. Also, what you need to do is you kind of need to save this to some kind of offline database, because lots of other subsystems actually need this data because they want to know what is the state of the spacecraft. So this is an example for a telemetry view. So this is one software that we use. It's called Geckos, and you can see here a number of telemetry packets. So, for example, there are a few confirmations that some checksum was correct and that some ping was actually received and was being worked on. Okay, so and it was executed. It's timestamped, and you get some additional information. And this is sort of the most basic thing you can really see. Once you know the state of your spacecraft, you actually want to command the spacecraft to do something. This is done via telecommands. And on the picture here, you can see some commands that have been executed and also some that are still to be executed. So, for example, on the upper link, in the upper part, you see a few pings which were not actually answered by the spacecraft, but the last one was received and was replied to. And the operator can, for example, already load a few telecommands on the manual command stack, prepare them, and then execute them very quickly. This is the lower part. Notice that these telecommands are very specific to the spacecraft because they really need to do something there. So this is in some way provided by the satellite manufacturer, and you have to somehow understand all the possible things you can do. In particular, you very often don't really want to do like very atomic things, but instead you want to achieve a certain task. For this, you bundle the telecommands. You can add, for example, also telemetry checks, so conditions on the telemetry, and you call this a flight operations procedure. So this will be sort of a bundled thing that will execute it on the spacecraft for the purpose of achieving a specific goal. Another thing that's important, as I've mentioned various times, you don't see the spacecraft all the time, meaning you cannot really command it all the time. But instead, what you do is you send telecommands, but you make them time-tagged, and then they get executed, for example, when you don't see the spacecraft. Okay, and these kinds of telecommands are called TTC. Let's look at an example. So this might be a set of time-tagged telecommands for a maneuver. Okay, so at time t0, we want to execute some maneuver, so we want to turn on the thrusters. This time and the position and the duration of the burn, they were calculated by the flight dynamics departments, of course. But 1 hour before that, we actually need to check, for example, that the spacecraft is in some fixed state, some prepared safe state. 8 seconds later, we might actually start heating up thrusters because the fuel needs some kind of operational temperature. Then 11 minutes before the burn start, you will automatically command the switch on of some additional telemetry. So this is kind of like you turn on the debug mode. Okay, you just tell the spacecraft to actually give you more data. Then because the burn will actually make the spacecraft shake quite a bit, there will be lots of alarms going off. So at some point before the burn, you will turn off these alarms, these safeguards, just because the direction of the spacecraft is actually expected. Then you start rotating in the right direction, of course, and at some point the burn starts. Now this should, in principle, stop automatically. However, you might command an additional safeguard stop command, just to make sure that in case the other one, didn't get executed, you stop nevertheless. And then you kind of reverse the whole procedure to return to a mode where you can proceed with your payload operations. Okay, and this would be a sequence of time-tagged commands that are uploaded to the spacecraft during an uplink, and then executed whenever T0 was actually taking place. All right, so there's one other thing that I want to describe, and this is mission planning. So it's probably one of the lesser known subsystems, and this is sort of at the point where you have to wait between automation and manual commanding. So suppose you have a scientist that actually wants to take pictures, so he wants to have the satellite taking some pictures of some region, so then he has to sort of ask if the satellite can do this and has to make a reservation. This is been taken care of by the mission planning system, which will then talk to flight dynamics to see whether this is actually possible, give feedback to the scientists, and this will also tell the operators or the operating, the telecommand operators to actually execute some command to take the data take. However, because of all these kinds of little issues, problems that you can have all the time, you cannot really automate everything. There is some kind of some amount of manual commanding that's still being needed. For example, due to those contingencies. So what the mission planning system internally does is it schedules activities, and it tries to do this in some consistent and conflict-free manner. Yeah, so imagine, for example, for the data take, you need to actually take the picture before you want to downlink it. Okay, so those are two activities, and they should actually take place in some order. Okay. From these kind of activities that were requested by some scientists, the system creates a timeline, which is then provided to everybody who needs to know what the spacecraft is going to do at some point. So here's one example. So that's one software that we use. So it's called Pinta, and it shows on the x-axis the time, and up on the top you see these black-white things. Okay, so and these are actually eclipses. So whenever the spacecraft is not in the sun or is in the sun, you can see this there. And below that there are a few experiments planned, but one of them is partially planned during an eclipse, but it has the condition that it must not take place during an eclipse. So this gives a conflict. Okay. And the mission planning system is responsible for identifying these kind of conflicts and actually supplying that information to the scientist or the operator to be resolved. One other thing you can see is this thing that we talked about at the beginning. So you need to downlink the information from the experiment. So you need some scheduled downlink opportunities, and you can see two of them actually as the green lines above the blue ground. So this is when the next time when the satellite actually sees the ground station and it can downlink the results of the prior experiments. Okay, so now we are doing kind of semi-automated all our experiments. We gather a lot of scientific data, but at some point everything has to end. So there's also the end of the mission that you have to consider. So in general, the mission time of a spacecraft might depend, for example, on the mission goal. Imagine that you have one specific experiment that you want to do, and this might be finished at some point in time. Also, it might depend on the orbit itself. Yeah? So if you have a spacecraft in an altitude of 300 to 400 kilometers, it will actually descend into the atmosphere within less than a year. If you have a satellite at an altitude above, say, 700 kilometers, it will take more than 25 years to actually get down. If you are on a geostationary orbit, you will actually never come down. So another thing is, and this is mainly for geostationary orbits, geostationary satellites, is that you have an finite amount of fuel. So at some point you can't really keep your spacecraft at the position where it is. So then you have to end the mission, of course. For geostationary satellites, this might take something like 15 years. For low Earth orbit satellites, a few years are pretty common, but very often you can actually extend the lifetime quite considerably if you are very careful about your fuel consumption, for example. Now, what are you going to do once you reach this end of the mission? Well, this depends again on the orbit. So, for example, if you have a low Earth orbit satellite, then you reserve some fuel, or you might reserve some fuel in order to actually take it to a lower orbit, such that it deorbits and disintegrates in the atmosphere within something like 25 years. These 25 years, they are nowadays pretty much mandated by, for example, the FCC and also the ESA. So you really need to kind of dispose of your spacecraft at most 25 years after the end of your mission. So you can deorbit LEO satellites, but usually there's not enough fuel to deorbit a geostationary satellite. In that case, you will actually raise the altitude by something like 500 kilometers and put them on the so-called graveyard orbit. Because that's a place where they are not disturbing anybody anymore. So you can put them there and, well, kind of forget about them. Okay. Well, and then you can look back at your mission. You have spent quite a few years on that, yeah. Well, hopefully everything was working correctly. You produce a lot of scientific data. You're happy, and with this, I also want to end my talk. So thank you very much, and enjoy the rest of the Congress.
Thank you. There's about 10 to 15 minutes left for Q&A. This works pretty simple. You walk to a microphone, you wave your hand, and you may end up with the opportunity to ask a question. This gets me to the asking questions bit. Q&A is for questions, not about statements or how nice the speaker was, etc. So keep it short. And the first question goes to the internet, to the Signal Angel, who has been diligently monitoring IRC and Twitter on the hashtag whole C. So, Signal Angel, do we have a question?
Yes. Hello? Yes. No mic! Hello? Need mic on the Signal Angel! Hello, check.
You need to use the microphone. Get the microphone, I will give the question first to this microphone over here.
Yeah, okay.
Hi. Hello? Is this on? Nope. Microphone 2, please. It's not on?
Number 5.
Is it?
Oh.
Is it on now?
Okay, great.
Test. Would it be feasible to put like false satellites in geostationary orbits as communication relays, so we have uplink all the time? And why is it not done?
Yeah, so this is feasible, and this is actually being done. So, for example, the ISS, as far as I know, actually does most of its communication via some relay satellite in geostationary orbit by NASA, but there are also, for example, European alternatives. Okay, so there's a European data relay system, for example, that you can also use for this. This is being used. However, it's always, money is always an important issue. Okay, so if you're using somebody else's communication relay system, then you, of course, have to pay for that. So you very often actually try to, well, find a minimal solution to your communication needs. Thank you.
Okay, next question goes to microphone number 2.
Yes, this is a question from the internet, which would like to know about the security of the protocols, in particular encryption or anything like that.
Okay, so I can't really give too many details about this because that's not my particular area of expertise, but in principle, the telecommanding or at least the telemetry is usually encrypted. So there's a lot of effort put into that. However, for the payload data, this is not always encrypted. For example, very famously known are the weather satellites. Yeah, you can just receive the data and it's transmitted in clear, and you can just receive them. Okay, thank you.
Okay, next question is for microphone number 1.
Thank you. At the certain point in your presentation, you told an example of the geosat that didn't fall down or didn't work. To whom goes the final decision of, oh, it's not working and we're going to drop this project and maybe start new? Who gets the final decision? And in particular, this geosat, well, it was put on an orbit so long ago. Did they just leave it there? It's down and it's breaking down, I suppose, but So one question is who gets the decision, and the other one is did they leave it there?
Yeah. Okay, so the decision-making process is kind of involved. I haven't been part of any mission yet that failed, so I kind of don't really know the details on that. But in principle, there's not just the flight director. So for example, I mentioned the flight director, but that's actually the person in charge during the actual operations. But there's also, for example, the project investigator, so the PI, who's doing the scientific, who's in charge of the scientific process. There are other kinds of organizational people, and they decide this together in some way. Okay, so this is a non-trivial decision. And regarding the other question, they could still, for TVSat-1, they could still control the satellite. Yeah, so they were actually able, as far as I know, to lower the orbit to actually have it burn up at some point. I think they even tried to turn it on at some time later, and I think it still worked. But nowadays, I think it is already burned up. So at least this mentioned somebody. I'm not quite sure, but yeah, it was still usable. Well, in that sense, you could still lower the orbit. So that's not a problem for the satellite.
Okay, next question for microphone number 2.
You mentioned you had a temperature time series on your charts. I was wondering, what methods do you use to find anomalies in this temperature time series?
Pardon? What's the question?
What methods do you use to find anomalies in that temperature time series?
Well, so I mean, there are quite a few properties of the spacecraft that might actually deteriorate over time. And there might be various indications for that. And you try to look for hints that something is wrong, something that you're not noticing because nothing is failing yet, but you actually want to see that, for example, some sliding average is actually increasing over time. Yeah, it's still below some kind of alarm limit, but it's actually getting worse. Okay, so you try to do time series analysis for that. Yeah, and there are various similar issues that you want to identify.
Okay, so that would be moving average or ARIMA.
So this particular example, or?
Yeah, I was wondering.
Well, I'm not sure this particular example shows anything particular. So this seemed to work properly, I guess. Yeah. So.
Okay. Thanks a lot.
Questions for now? Sorry. Next question is microphone number 1.
You spoke about commands and sending commands. Does these commands get sent and interpreted by the server, or is some kind of compilation, and you send a binary or something like that, unexecutable? Do you ever server-side interpret, server-side, right? Supply-side interpretation, or you send a compiled command, a software?
Okay, well, it's kind of like an API that you define that actually gets provided by the satellite manufacturer. So you really send a binary command. So it might be these protocols are actually very effective. Yeah, so they do just one thing. They make sure that this is actually transmitted correctly, and then it gets executed. So this might be just switch one of the machines. Okay, so there's just some binary thing that you need to transmit to the satellite. There's of course some level of checking going on. So for example, there might be a command counter that needs to be correct or some kind of checksum. But apart from that, this will be executed directly. However, sometimes you also need to upload some kind of binary data. For example, imagine that for some reason one of the things on your satellite moves a little bit. Then the orientation is not correct anymore, and you need to somehow fix this in your internal calculations. For that, you need to actually upload some rotation matrix, for example, describing this small distortion. Okay, so in that case, you would actually upload some binary data that gets put at the correct place on the onboard computer.
Okay, next question is for microphone number 4.
About the orbits, is there much garbage on these orbits, and is this a problem?
Is there a what? Sorry.
Is there much garbage, so old satellites or parts that get lost?
So you're talking about space debris, so stuff that's flying around and that might actually hit our satellite. Yes, there is quite a bit. So satellites actually have to do maneuvers to just to be on the safe side, to not crash into some, to not collide with some space debris. It's getting more and more. In particular, there was a destruction of a satellite a few years ago by the Chinese, so they tried to blow up their own satellite. And for example, this created a lot of additional debris. This is, however, the debris is actually flying on the same orbit, or approximately the same orbit as it was beforehand. Okay, so instead of a large target, you now have many smaller ones. They are being tracked by various space agencies, and you can actually get this data online somewhere. And I think they will even write you an email if your satellite happens to be on a collision course with something.
Can I ask a second question? Is there any idea how to remove this? Or
So I'm not too knowledgeable about this, but in principle there are people trying to do this. So the ESA actually has various projects, has done a few conferences on the question how to deal with space debris. But I'm not sure there's any really good and feasible solution yet. But maybe in a few years, hopefully.
Thank you.
Thank you.
Okay, next question is from microphone number 5.
Yeah. I would like to add to her question. So she was talking about the Kepler syndrome in the LEO, right? But you also talked about the graveyard orbit.
Yeah.
So will we build a second Kepler syndrome just a little further out?
So I'm not sure I got the last question, but so the graveyard orbits, they're actually for geostationary orbits, yeah? Because you can't deorbit a satellite from there. So instead you kind of move it away from the Earth.
Yeah. So my question is, will we create the same problem on the geostationary disk?
Yeah, I mean, in principle, this means that there is also space debris then there in geostationary orbit. However, I mean, if you fix the orbit, then, well, with increasing orbit, there's more space left, okay? So the density actually kind of reduces with larger radius. So you're not having the same problems as with LEO. Yeah? So because in LEO, they're really you're accumulating space debris faster than you're actually deorbiting it. So and you have to actually go through LEO to get to geotransfer orbits. But yeah, it's not such an urgent issue there, and likely will never be. But who knows? Also, maybe also some comment. Nowadays, there's kind of a shift from geostationary orbits to actually going more LEO. Yeah, also for communication satellites. So this might actually, maybe in long term, even reduce the number of geostationary satellites. But I don't know.
Okay, next question goes to the internet.
So IRC, hello? What? Yes, hello. IRC would like to know if you're concerned with the SpaceX launching 5,000 satellites into low Earth orbit running at 25,000 kph.
Pardon, can you repeat that?
SpaceX is talking about launching thousands of small satellites.
Mm-hmm. Yeah.
How is that going to work with communications with those buzzing around in low orbit?
So I don't know the details about this project, but so as far as I know, they talk about something like 4,000 communication satellites in lower Earth orbit, and as far as I remember, they're supposed to communicate via lasers. Okay, so they will actually span sort of a laser communication network, and then you just try to route the information that you have through this network. Okay. Of course, this is a lot of satellites. I don't know at which altitude they will operate, whether this will cause problems for anybody. But as far as I know, the FCC in the US has already said that it's okay to proceed with this project. So yeah, let's see where this will lead. It's hard to say at the moment, I guess.
Next question is for microphone number 3, and this may be the last question.
I would like to know, in regard to redundancy with antennas, are the satellites built in a way that an antenna for one frequency can take over duties that were actually intended for another frequency, especially in 2 scenarios, if the antenna receiving instructions is compromised and cannot deploy, or, for example, if the telemetry antenna is somehow incapacitated.
Right, so on the ground, for example, an antenna might actually be able to serve another frequency, okay? So this is pretty common. For example, in Weilheim, one of the pictures you've seen a large antenna that can actually serve multiple frequencies. On a satellite, I don't think this is actually done as far as I know. However, of course, you could try to route the same kind of information through another antenna, but it depends a little bit on the bus, I guess. So, for example, of the satellite bus. So, on some satellites, the additional antennas are actually kind of separate from the satellite bus, and in that case, it's not feasible to actually route the telemetry through that. But I guess in various cases this is indeed possible, but I'm not sure. I've never heard that this is actually being used.
Okay, thank you very much. That was the last question, and this was the end of this talk. A round of applause for our speaker.
Thank you.